Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Welcome back to our lecture. Second part on chapter 5, mass, Bernoulli and energy equation. Previously, we have learned about the Bernoulli equation, which is, I hope everybody can still remember the equation. Now, for this week, we will learn more on the another part of mechanical energy that can be added into Bernoulli equation. Okay, if you remember previously, I said that Bernoulli equation has limitation because Bernoulli equation cannot be used if there is a turbine, a pump, and any losses in the pipeline. But for this week, we will learn on how to add those parameters into flow equation. Okay, first let's go about mechanical energy and efficiency. Okay, mechanical energy is the form of energy that can be converted into mechanical work completely and directly by an ideal mechanical device such as an ideal turbine. Okay, mechanical energy of a flowing fluid per unit mass. Okay, the mechanical energy can be P over rho plus V squared over 2 plus Gz. Okay, because it's come from the flow energy plus the kinetic energy and the potential energy. And then you can see the mechanical energy equation. Okay, so there is two devices that we will learn today. Is about the pump and turbine. Okay, pump and turbine is two different devices, which is the similarity is both have the shaft work. Okay, they transfer the mechanical energy, either mechanical energy to electrical energy or electrical energy to mechanical energy. So for pump is a fan receive a shaft work usually from an electric motor. Okay, so pump convert from electrical energy and transfer it to the fluid as mechanical energy. So pump convert from mechanical energy to electrical energy to mechanical energy. While for turbine converts the mechanical energy of a fluid to a shaft work, or normally it's go to electrical energy. In general energy equation, we have learned for the I hope that when you see the Q plus W equal to dE over dt, you can remember it from your thermodynamics. So from your thermodynamics, you consider the heat transfer, the work transfer, and what is the effect of those into the mechanical energy from the system. Okay, but for the heat, all about the heat transfer, we're not considering the fluid mechanics. Okay, so what we consider here is just the energy transfer by work. So for the work, the total work can come from the W shaft, work from the shaft, pressure, viscous on another. Okay, then from this equation, which we know that enthalpy is equal to internal energy plus pressure over density, then we can produce this equation. From this is we ignore the heat transfer. Okay, as I said before, so we just focus on the work shaft. Okay, work shaft in plus the effect of pressure, velocity, and also the potential energy. Okay, and then because we shaft, two main equipment in work shaft is pump and turbine. So we include pump and turbine in the equation, and also the mechanical losses, which will normally will happen in any flow system. So we got and at the end we got this equation. Okay, P P1 plus OG plus V1 square over 2G plus Z. Okay, I think you remember that you will see this on the Bernoulli equation. But what we add is hash pump and hash turbine plus HL. Okay, hash pump at the left of the equation and hash turbine and losses at the right of the equation. Okay, this slide is very important. As I told before, there is no equation given in the final exam, so you need this slide, or either you remember or you will need this slide to answer for your final exam. Okay, so first the energy equation. Okay, this one is the energy equation, and then for pump, okay, what given here is the hash pump, the head of the pump. To get the work for the pump, the equation is W pump equal to m dot G hash, m dot for mass flow rate times G times hash pump. Okay, or density times G times V dot the flow rate plus times hash pump. Okay, this is the equation to get the work for pump. The work for pump, from the input for hash pump, you also can get the pressure rise by the pump, which is delta pump equal to OG hash pump. And then from these two equations, you can conclude that to get the work for pump is equal to V dot, the flow rate, times the pressure difference, the pressure rise because of the pump. And then for turbine, okay, to get the work for the turbine is equal to m dot, the mass flow rate, times G times hash turbine, which you can get from here. Or alternatively, you can use the equation for density times G times flow rate hash turbine. Okay, m dot is equal to density times V dot. Okay, that's why these two equations come from. Or you can get the pressure drop by the turbine. Delta P turbine is equal to OG hash turbine. Okay, it's the same from the pump and also the turbine. And then there is a losses hash L. Okay, what you get here is the units is in meter, but if you want the units in the energy, okay, mechanical loss energy is equal to m dot G hash L, or density times G times V dot times hash L. Okay, it is just the same, W pump, W turbine, and also the energy on the mechanical loss. Okay, I hope this figure can describe on this part. Okay, initially what you use is the Bernoulli equation, which is Bernoulli equation didn't consider any work from the shaft, from the heat transfer or anything. As when we include here, okay, from the pump, turbine, and also losses, okay, work from pump will become another energy for the flow rate, while for the turbine and the mechanical losses, it is where the energy goes from the system. Okay, another factor you need to consider here is the kinetic energy correction factor, alpha. Okay, normally alpha is 2.0 for fully developed laminar pipe flow, or alpha can become between 1.04 to 1.11 for fully developed turbulent flow in a round pipe. Okay, but for the value for the kinetic energy correction factor will be given in any equation. Okay, so for your equation, okay, this is the final version of the equation. P1 plus OG plus alpha 1 V1 square over 2G plus Z1 plus hash pump equal to P2 over OG plus alpha 2 V2 square over 2G plus Z2 plus hash turbine plus hash losses. Okay, we go to the first example to use this equation. Okay, water is pumped from a lower reservoir to a higher reservoir by a pump that provides 20 kilowatt of useful mechanical power to the water. The free surface of the upper reservoir is 25 meters higher than the surface of the lower reservoir. If the flow rate of water is measured to be 0.03 meter cube per second. Determine the irreversible head loss of the system and the lost mechanical power during the process. Okay, so this is a good question. The distance is 25 meter, and it is they give the power of the pump 20 kilowatt. Okay, and then the flow rate is 0.03. Okay, let's solve this equation. First, this is the general equation for power equation, and then for this case, okay, I change the pointer to the pen. Okay, we need to consider first point and second point. So first point is at the surface of the lower reservoir, and the second point is at the surface of the upper reservoir. So for the lower reservoir, you know that this surface is open to the atmosphere. So from the equation, we can consider P1 over G is 0. Okay, and then this is an open surface where the area can be considered as too big because it's a reservoir. You can the area is too big, so the velocity can be negligible because the velocity can become almost 0. And then Z1, okay, for Z1 and Z2, you need to consider by yourself. Okay, for me, I prefer for the lower part become 0 and the higher part become the number of the h of the point. So for point 1, h is equal to 0. Okay, so okay, I can cancel for this part. So hp equal to, okay, for the second location, P2 is open to the atmosphere, so P2 is equal to 0. The area is too big. We can consider the V is also almost 0. And then Z is equal to 25. Turbine, there is no turbine in the system. You can neglect it. Plus HL. Okay, there is HL. So the equation become HP equal to Z2 plus HL. Okay, the equation give the W for the pump. Okay, so you can use the equation W equal to OG V dot HP. Okay, you manipulate this equation, you can get the HP equal to W over OG V dot, and then you got the HP, the head of the pump become 67.9 meter. For the head pump, okay, you can just search from the Shopee or Lazada or anything, and then you can see that for pump, okay, what parameter given for any pump, commercial or any commercial pump is the head pump. Okay, this is where the head pump come from. Okay, so you get the HP equal to H pump is equal to 37.9 meter. Okay, then using the equation, HP is equal to 67.9, Z is 25 meters, and HL is the one that you are searching here. So you got the HL equal to 42.9 meter. Okay, that's all. No, sorry. The second part is the mechanical losses. Okay, how much the energy mechanical losses. So the equation is OG V dot HL, and the CT is 1000, G is 9.81. V dot is 0.03. 42.9 is the head losses you got from the calculation before. So you got now the mechanical energy losses is equal to 12,642 watt. Okay, I hope you can understand. Okay, we go to the second example. Okay, the water level in a tank is 20 meters above the ground. A hose is connected to the bottom of the tank, okay, and the nozzle at the end of the hose is pointed straight up. The tank is at sea level and the water surface is open to the atmosphere. If the line leading from the tank to the nozzle is a pump, okay, there is a pump here, which increase the pressure of the water. If the water jet rises to a height of 27 meters from the ground, determine the minimum pressure rise supplied by the pump to the water line. Okay, So the equation is you need the minimum pressurized supplied by the pump to the water line. Okay, again you use the same equation, P1 over G plus alpha, okay. And then, okay, we consider for point 1 and point 2. For this case, for me, I think the best is point 1 is at the water surface, and point 2 is the highest point of from the water jet. Okay, for point 1, P1 is, you know that it is open to the atmosphere. Then, okay, you can cancel the pressure effect. And the area is too big. So the velocity can be almost 0. You can cancel for this part. Z1 is 20 meter. H pump. Okay, there is a pump. So, okay, you need the H pump. Okay, for point 2 is up here. It is open to the atmosphere. P equal to 0. And V is also 0, okay, because this is the highest point where the velocity is 0 at that point. Okay, Z2, there is, okay, Z2 is 27 meter. Turbine, there is no turbine. Losses, okay, that one, losses, okay, are we searching for losses? Oh no, okay, so you can cancel also the losses. So the equation becomes Z1 plus HP equal to Z2. Okay, Z1 is 20, Z2 is 27. Then H pump it become, you can get a H pump is equal to 7 meter. Minimum pressure supplied by the pump. Okay, the equation is delta P equal to OG H pump. Okay, you got all the value. Density is 1000, G is 9.81, and H pump is 7 meter. So delta P is equal to 68.7 kilopascal. I hope you can understand. Okay, we go to the third example. Okay, for this example, consider a river flowing toward a lake at an average velocity of 3 meters per second. Okay, for these cases, it is a river and the flow rate from the river go into the system. So there is V1. V1 equal to 3 meters per second. The rate is 500 meter cube per second. Okay, this is V dot at a location 90 meter above the lake. Okay, the H difference is 90 meter. Determine the total mechanical energy of the river water per unit mass and the power generation potential at the entire river at that location. Okay, again, same with before, start with the equation and then find anything that you can cancel from the equation. Okay, from the water surface here, from the river surface, P equal to 0. Okay, velocity is given here, 3 meters per second. Z is equal to 90 meter. Pump, there is no pump, so you can cancel the HP. For the point 2 here, it is also still open to the atmosphere, then P equal to 0. The V is also almost 0 because the area is too big. Z can become 0 if you consider Z1 is 90. Turbine is the one that we are searching, and HL, okay, there is no losses given in the system, so you can ignore the H losses. So the equation become alpha V1 square over 2G plus Z1 equal to HT. Okay, so you can get the HT equal to 1 is for the alpha because there is no information about the alpha in the form of this equation. So you can consider alpha equal to 1. V1 square is equal to 3 meters per second over 2G 2 times 9.81 plus Z1, okay, plus 90. You got that HT become 90.45. So to get the power of the turbine, W equal to rho GV dot H turbine. Okay, you got all the information. Rho equal to 1000, G 9.81. V dot, okay, V dot is given here. V dot is 500 meter cube per second time H turbine. Okay, you have calculated before. H turbine equal to 90.45. So you got that the work from the turbine is equal to 443.6 megawatt. Okay, let's go for the, I didn't remember, I think this is a fourth example. Okay, water flow at a rate of 20 liters per second through a horizontal pipe whose diameter is constant at 3 centimeter. Okay, diameter here is 3 centimeter. Okay, you see here the flow rate is given in 20 liters per second. I hope you are available. You can convert it into to become meter cube per second. You know that 1 meter cube equal to 1000 liter. Is it right? 1 meter cube. Okay, 1 meter cube is 1000 liter. So 20 liter per second is equal to 0.02 meter cube per second. To a horizontal pipe whose diameter is constant at 3 centimeter. Okay, the pressure drop across the valve in the pipe is measured to be 2 kilopascal. Okay, the pressure drop is 2 kilopascal. Determine the irreversible head loss of the valve and the useful pumping power needed to overcome the resulting pressure drop. Okay, using this equation again. Okay, and then find out which one you can cancel from this equation. Okay, P. Okay, they given that P1 and P2. Okay, the difference is 2 kilopascal, so you cannot cancel the P. Okay, for velocity, will there be a difference from the velocity? When the pipe is 3 centimeter in and out, so the velocity is the same. So you can cancel for the velocity part. Okay, it does not mean that there is no velocity. There is a velocity, but V1 and V2, the value is same. Okay, it is a horizontal pipe, so there is no elevation. Z1 and Z2 is same. You can cancel Z1 and Z2. There is no pump, so you can cancel HP. There is no turbine. You can cancel H turbine. So the equation become P1 over OG equal to P2 over OG plus HL, or HL is equal to P1 minus P2 over OG. The value for P1 over P2 is 2 kilopascal or 2000 pascal. Density is 1000, G is 9.81. So you got the HL equal to 0.204. Okay, irreversible head loss. Okay, the second question is useful pumping power needed. You already know W pump equal to V dot time delta P. So V dot equal to 0.02 time delta P is 2000. Then you got that. Work pump needed here is 40 watt. Okay, the next example again. Okay, there's a lot of example. You can pause the video anytime you want if you want to ask. So, okay. A large tank is initially filled with water 2 meters above the center of a sharp edge 10 centimeter diameter orifice. Is there any figure or there's no figure? Okay, you need to imagine by yourself. Okay, a tank. Then 2 meters. Okay, what the water level is 2 meters, and there is a sharp edge 10 centimeter diameter orifice at the bottom. The tank water surface is open to the atmosphere and the orifice drain to the atmosphere. Okay, so for the water surface is open to the atmosphere and the orifice also drain to the atmosphere. If the total irreversible head loss in the system is 0.3 meter, determine the initial discharge velocity of water from the tank. Take the kinetic energy coefficient factor at the orifice to become 1.2. Okay, again, using the same equation, you know that okay, the water surface is open to the atmosphere, the orifice drain to the atmosphere. So P1 and P2 can be cancelled. Okay, it is a tank, so you can consider the velocity V1 is equal to 0. Okay, Z1 is 2 meter, HP, okay, there is no pump. V2, okay, the orifice is 10 centimeter diameter, so you can get V2. Z2, okay, Z2 can be considered to 0 because Z1 is 2 meter above the Z1. There is no turbine. There is a head loss of 0.3. So the equation becomes Z1 equal to alpha V2 square over 2G plus HL. Okay, V2 equal to 2G, just manipulation from this equation. Put all the information you got, and you got that V2 equal to 5.27 meter per second. Okay, you got the initial discharge velocity of water is 5.27 meter per second. Okay, the next part is on mechanical efficiency of a device. Okay, first you just calculate the energy. Now we also need to consider the mechanical efficiency. Okay, the effectiveness of a conversion between mechanical and static and the mechanical energy of the fluid is expressed by the pump efficiency and turbine efficiency. So mechanical efficiency, okay, this is the equation for mechanical efficiency. The mechanical efficiency of a fan is a ratio of the increase of mechanical energy of the air to the mechanical power input. Okay, for pump, okay, because a pump is a fan receive the shaft work, okay, so pump receive the power from the electric and then convert it into mechanical energy. So for an efficiency of a pump is mechanical energy, mechanical power produced by the pump over the mechanical power input. Or for this one is the electrical supplied to the pump. And then for the turbine, you know that turbine is converting mechanical energy to the shaft work, mechanical energy to the electric. So for efficiency of turbine is mechanical power output or the electric power output from the turbine over the mechanical power decrease of the fluid. Okay, mechanical power input. You calculate from your equation. The WT is here. Okay, so for pump or generator, normally it is a combination from two devices, from turbine and also the generator. So you can calculate each motor and generator efficiency. Okay, for the motor efficiency is a mechanical power output over the electrical power input, while for the generator it is the electric power output over the mechanical power input. Okay, and then you can get the overall efficiency. Okay, the combination for the turbine and generator is equal to efficiency of the turbine times efficiency of the generator. Okay, for the efficiency, the value 0 and 100%. Okay, if it is 0%, then the conversion is there is no conversion at all. But for 100%, the conversion is perfect conversion. Okay, other information I think okay, you can read by yourself. Okay, we try the first example. Okay, in a hydroelectric power plant, 100 meter cube per second of water flows from an elevation of 120 meter to a turbine, where electrical power is generated. The total irreversible head loss in the piping system from point 1 to point 2 is determined to be 35 meter. Okay, this is the HL. HL is equal to 35 meter. In the overall efficiency of the turbine generator is 80%. Okay, the combination is 80%. Estimate the electrical power output from the turbine. Take the density of water is 1000 kg per meter cube. Okay, almost all information is given in this figure. So again, from the same equation, the first point at the surface of the upper reservoir, and the second point is at the surface of the lower reservoir. So you can consider P is equal to 0, P2 is equal to 0 because it is open to the atmosphere. And both point is located at the area that is too big. So you can consider the V1 and V2 is almost 0. There is no pump. HP, you can cancel HP. Okay, there is a turbine HT. Okay, Z2 you can consider is 0 because Z1 is 120. HT, there is a turbine. HL is also given that HL is equal to 35 meter. So Z1 equal to HT plus HL. Okay, what you want to search is HT. HT equal to Z1 minus HL. HT is 120 minus 35 equal to 85 meter. So for turbine, the work of turbine is equal over G V dot H turbine. Rho is 1000, G is 9.81, V dot is 100 meter cube per second given here. And HT you have to calculate, HT is 85. So you got the work turbine is 83,385 watt. So the overall efficiency the overall efficiency is 80%. So you can calculate the electric power generated. W electric equal to overall efficiency is 0.8, and work turbine, the mechanical work turbine is 83,385 watt. So you got that. The answer is the electric power given is 66,708 watt. Okay, just to check before. Oh, I think I made a mistake in the slide. This is kilowatt. Okay, and for this part, this is this is kilowatt here. Okay, so 66 is 66.7 megawatt. Okay, the next example, performance of a hydraulic turbine generator. Okay, the water in a large lake is used to generate electricity by installation a hydraulic turbine generator at a location where the depth of water is 50 meters. The water is to be supplied at a rate of 5,000 kg per second. If the electric power generated is measured to be 1,862 kilowatt and the generator efficiency is 95%, determine the overall efficiency of the turbine generator and the mechanical efficiency of the turbine and the shaft power supplied by the turbine to the generator. Okay, this okay. So first, okay, same using the same equation. Okay, you know that for the point 1 and point 2, it is open to the atmosphere. So P1 and P2 can be cancelled. Okay, alpha, okay, V, okay, then velocity 4.1 is also can be considered to become 0. Okay, V2, okay, also can become to 0. There is no pump. There is the turbine and the head losses. Is there any losses? Okay, the question didn't give any information about the head losses. Okay, Z1 equal to HT. Oh, okay, I forget to cancel for Z2. Okay, because we consider Z2 is 0. Okay, Z1 equal to HT. HT, the head of turbine is 50 meter. To calculate the work turbine, m dot g hash. Okay, because why we use the m dot g hash? Because it is given here. The mass flow rate is 5,000 kg per second. So it's easier to use the m dot g hash. So m dot is 5,000, g is 9.81, and hash turbine is 50 meter. So you got the work turbine is 2,450 kilowatt. Okay, so you got the efficiency of all is given which is 95%. Okay, but before that you need to know the overall efficiency. Okay, overall efficiency it is given that the power generated is 1,862 kilowatt over the mechanical power generated from the turbine is 2,450. So the overall efficiency is 0.76. Okay. Okay, you got the overall efficiency, and then the second is the mechanical efficiency of the turbine. Okay. You have seen this equation before. The overall efficiency equal to efficiency of the turbine times efficiency of the generator. So efficiency of the generator is given here, 95%, 0.695. So you got the hash turbine equal to 0.8. Okay, we go to the next, okay, I hope you can get from this question. Okay, so C, the shaft power supplied by the turbine to the generator. Okay, you have answer here. W turbine is 2,450. Okay, the next example, electric power is to be generated by installing a hydraulic turbine generator at the site 70 meters below the free surface of a large water reservoir that can supply water at the rate of 1,500 kg per second. Okay, the equation is almost same with before. If the mechanical power output of the turbine is 800 kilowatt and the electrical power generation is 750 kilowatt. Okay, for this question, it's given earlier that the mechanical power output is 800 kilowatt and the electrical power generation is 750 kilowatt. Determine the turbine efficiency and the combined turbine generator efficiency on the plant. Neglect losses in the pipeline. Okay, using the same equation, you know that the first point is at the upper reservoir, the second point at the lower reservoir. It is open to the atmosphere. P1 and P2 can be cancelled. The surface is too large, so you can cancel the effect of kinetic energy, or V. And then Z1 is 70, there is no pump, you can cancel HP. Z2, okay, Z2 is 0, okay, there is turbine, and the losses, neglect losses in the pipe, okay, HL. So Z1 equal to HT, so HT equal to 70 meter for work turbine, M dot G hash turbine. Okay, M dot is given here, 1,500 kilogram per second. 1,500 times G, 9.81 times hash turbine, 70 meter equal to 1.03 megawatt. Okay, it is given that the mechanical electrical power generation is 750 kilowatt. So you can get the overall efficiency. 750 over 1030, the overall efficiency is 0.728. And then for the turbine efficiency, okay, work from turbine is 800 kilowatt given here, and the mechanical work from mechanical energy is 1030 kilowatt. So you got the efficiency of a turbine is 0.777. Okay, next question. Water is pumped from a lake to a storage tank 20 meter above the at a rate of 0.07 meter cube per second, while consuming 20.4 kilowatt of electric power. Disregarding any frictional losses in the pipes and any changes in the kinetic energy, determine the overall efficiency of the pump motor unit, the pressure difference between the inlet and the exit of the pump. Okay, again, the same equation. Okay, for the storage tank is also open to the atmosphere. Okay, this is the second point. This is the first point. Okay, first point is open to the atmosphere. You can cancel P1 and P2. The surface is too large. You can cancel V1 and V2. Okay, Z1 is 0 because Z2 is 20 meter. We can consider here. There is a pump. There is no turbine. Disregard any friction loss. Okay, you can cancel the HL. So HP equal to Z2 equal to 20 meter. Okay, Z2 is 20 meter. The power of the pump, W pump is rho G V dot HP. Rho is 1000, G is 9.81. V dot is given here, 0.07 meter cube per second. Time hash pump. Okay, hash pump you calculate before. Hash pump is 20 meter. The work pump is 13.734 kilowatt. Okay, to calculate the overall efficiency, okay, the mechanical energy is 13.734 and the electric power given is 20.4 kilowatt. So you got here the overall efficiency is 0.673. Okay, for the second question, the pressure difference between the inlet and the exit of the pump. Okay, for this both part. Okay, what is the pressure difference? You know this equation, delta P pump equal to rho G H pump. Okay, just put all the information you know. Then you got the delta P pump equal to 196.2 kilopascal. Okay, sorry. Okay, I hope you can understand this example. For this lecture, I think there is a lot of example is given. I hope you can understand and you can feel that the fluid mechanics subject is really, really easy. Okay. Okay, we go to the last example. Okay, the last example. Okay, before we just consider for the pump and turbine. So for this time, we consider for the fan. Okay, a fan is to be selected to cool a computer case whose dimension is 12 cm times 40 cm times 40 cm. Half of the volume of the case is expected to be filled of the component and the other half to be filled to be airspace. Okay, for this part, the dimension is 12 times 40 times 40. But half there is a component and the other half is to be airspace. Okay, so for the airspace is half of the dimension. A 5 cm diameter hole is available at the back of the case. Okay, so for here, the dimension is 5 cm hole. Okay. At the back of the case, for the installation of the fan that is to replace the air in the void space of the case once every second. So what the function of the fan is to deliver the air in the air zone, okay, air zone here, once every second. So you know that to get the flow rate, V dot is equal to the volume, the void volume over 1 second. Okay, small low power fan combined units are available in the market and the efficiency is estimated to be 30%. Okay, the efficiency of the fan is 30%. Consider the air density, considering the air density is 1.2 kg per meter cube and the kinetic energy coefficient factor to be 1.1, determine the wattage power and the pressure difference be across the fan. Okay, this is the important point from the question. Okay. So first, you know the air volume in the computer case is 0.5 or half of the volume here, 12 times 40 times 40. You got, okay, so sorry, this one is 960. 960. It's not easy to write using the mousepad. 960 centimeter cube, or you can convert from centimeter cube to the meter cube. Okay, I have teach you before. Air flow rate, you know that all the air here is flow every second. Okay, air replace every second. So the V dot is 0.0096 meter cube per second. Air velocity to the outlet. The outlet is 5 cm diameter. So, okay, the area is 0.00196 meter square. So, for the velocity is equal to V dot over A. Then you got the velocity is 4.9 meter per second. So, for fan power, okay, you use the, okay, let's go for the second slide. Okay, for the fan power, again using the Bernoulli, the energy equation. Okay, you know that 4.1 is from the open space. I mean, P1 can be considered to be 0. P2 can be also considered as 0. Okay, for V1, okay, V1, the air input to the system. Okay, it is from the outer space, and the velocity can be considered to be very, very low because the area is too big. Okay, there is horizontal, there is no effect of Z1 and Z2. There is a fan, there is no turbine. Is there any losses? Losses. Okay, there is no loss. There is, you can neglect the losses. So, okay, HF is equal to alpha V2 square over 2G. Given the kinetic energy coefficient factor is 1.1, V2 is 4.9 square, you have calculated before, over 2G, 2.981 equal to 1.35 meter. So work for fan, okay, is the same equation for work for pump. W fan is equal to rho G V dot H pump. Rho is 1.2, G is 9.81, V dot is 0.00696 times 1.35. Okay, you have calculated for HF. So work for fan is equal to 0.152 watt. So it is given here. This is the work needed for fan. However, you know that the wattage power of the fan motor you need to be purchased. Yeah, the motor efficiency is just 30%, 0.3. So efficiency is equal to W mechanical over W electric. So what you want to search is for the work electric equal to the work mechanical, which you have calculated here, divided by the efficiency of the fan. Then you get the wattage power of the fan motor to be purchased need to be 0.5 watt. Okay, hope you can understand. Okay, the last part is the pressure difference across the fan. Okay, again using the equation delta P fan equal to rho G H fan. So delta P fan equal to 1.2 times 9.81 times 1.35, the H fan. So you got the delta P fan equal to 15.89 Pascal. Okay, so that's all. Okay, that's all what we learned for this week. So as the summary, you got the Bernoulli equation. There is some limitation of the Bernoulli equation. You also learn about the hydraulic guideline and energy guideline. You also can consider, you can apply for the Bernoulli equation in several cases. You also learn about the general energy equation, energy transfer, the energy transfer, shaft work, and work done by the pressure force. And lastly, you also learn about the energy analysis of the steady flow, which include the efficiency and also the kinetic energy coefficient factor. Okay, that's all for this week. Thank you for watching.